Oh, howdy all, grab yourselves a beer. It's time for something a little bit different today. Now, those of you that have followed my channel for any period of time will know that it's about the online game Path of Exile, a game that I'm a little bit too obsessed with. But, like everyone else that has interests in one particular hobby, I've got a few other interests as well. And there's something that's been going around in the mathematics-related YouTube channels that caught my attention, which was the MegaFavNumbers hashtag that was going around. What that is just basically a thing where people are putting up videos about their favorite number that exceeds 1 million. So you can probably see a screenshot here of three numbers that are very related to each other and that I wanted to put up as my mega favorite numbers. So the origins of this was me getting nerdsniped. Nerdsnipe is a puzzle that is designed to sort of not particularly appeal to people except those with a particularly extreme determination not to be beaten by a puzzle. And I saw this a couple of years ago and I was like, you know what? I can solve this. I'm sure I can solve this. You know, I had a maths background. I studied maths at uni. I did an honours thesis in pure number theory. I'd been interested in maths for a long time. Surely I can get this out. Surely it can't beat me. And of course I got nerdsniped badly because there's probably only a couple of thousand people alive that can solve this problem. I believe that my honours thesis supervisor at the University of Sydney would be one of two people that were at the University of Sydney at the time that could actually solve this problem. It looks really simple. It is deceptively brutal. And the smallest answers to it are these three favourite mega numbers. So, you know, one of them's the apple, one's the banana, one's the pineapple. The reason that this, of course, looks so deceptive is that it's written in those sort of fruit math, in that fruit math setup that's designed particularly to sucker people like me in, because you're like, oh yeah, that's got to be easy. It's sort of written for Facebook, you know, it's for Facebook sharing. Of course it's going to be easy. So I went through the approaches to how I tried to tackle this. Of course, firstly, I got rid of all of the fruit and changed them into normal algebraic variables. And then noticed that everything's symmetric. Swapping A and B changes nothing. If A, B, and C are a solution, B, A, and C are a solution, B, C, and A are a solution, and so on. I thought, well, what if all of them are equal? What do you get if you put in, if all three of the numbers are equal? And what you get is a half plus a half plus a half, which is 1.5. Now that's miles less than 4. Now I know from experience with problems like this that the further away that you get from equality on the three different terms, usually but not always, the more extreme the value becomes. And in this case, that's correct. The further the three values get away from each other, the larger the answer is. So I was like, all right, what if we try 1 and 2, just to try and find an answer? Because the hard part of this problem is getting them all to be whole positive numbers. So I put in 1, I put in 2, and I kept looking and looking. Eventually I realized there was an answer between 11 and 12. I wasn't sure what it was, and so I consulted some computer software and worked out that it's 11.286 ... And there's no nice way to express that number. It involves the, I then worked out using various formulas that it has a closed form, but that requires complex numbers. It requires a nested square root of a negative number inside a cube root sign. So it's basically a really messy answer. And it doesn't help us find the answer that we're wanting. This path ends up being a dead end. But it looks like it's got some promise, so I was sort of like, oh yeah, let's just try things. I tried a bunch of other numbers. I didn't actually find the the whole number answer that's most easily found. Now this is not a solution to the problem because you'll notice that they have to be positive whole values. The solution that was found though was 1, 11, and -4. This is actually a really powerful step towards solving the problem, but it doesn't look like it. And that was a step that I didn't understand. So what I did then was I multiplied through to clear denominators. I multiplied both sides of the equation by a plus b, bracket a plus b, bracket a plus c, bracket b plus c. And this then gives us this expression that you see here lower on the screen. And let's just zoom in on that because some of you are probably watching this on mobile. And I realized at that point that I may have introduced false solutions as well, because there's nothing guaranteed about a plus b times a plus c plus times times b plus c being positive, at least to start with. It means that, for instance, you've just added a false positive where b is 0, a is equal to minus c. Now becomes a solution, whereas it actually isn't a solution to this. So anyways, I'm looking through this and I just can't see how to go any further. And I wasted far too much time on this problem. Eventually, along comes Google to the rescue. Google and a mathematician by the name of Amit. I don't really know anything about Amit, but he has had a look at this problem and has solved it. And what was really interesting was it was very close to the area that I did my honours thesis in, which was groups of elliptic curves on the groups of rational points on elliptic curves. Which, if that sounds like gobbledygook to you, that's fine. This was something I knew what that meant, but I was the only person in my honours year that could give a definition of what a group of rational points on an elliptic curve meant. And that was a necessary first step in order to be able to solve this problem. And even though I was in that situation of having that relevant information, I still couldn't solve it. And so where do we go with this? Anyway, Amit goes through and talks about how this is a deceptively difficult problem that is, probably, well, his estimate 1 in 20 million people can solve it, which would mean only 350 people around the world. I dispute that. I think it's probably in the multiple thousands, the number of people in the world that could solve this problem. It'd be anyone with a doctorate in maths that specializes in number theory could probably get this, or at least a large subset of them could. Anyways, the key to it is that what you want to do is recognize first that multiplying all of these variables by a set number, so we've got A, B, and C here. If you were to multiply all of them by 2, or multiply all of them by 3, or multiply all of them by 4, that doesn't actually change whether or not you've got a solution here. So for instance, if you found the solution 11, 1, negative 4, if you have found that solution, you'll notice that doubling it remain a solution. They're not the solution we want because they're not all positive whole values, but they do solve this first equation. Likewise, if you halve them all, if you triple them all, they remain solutions. And so he recognized from that you can express C as just being equal to 1 over AB, and just assume that they're all the same. And so it's an equation in 2 variables, not an equation in 3. And then you can use a complex bit of mathematical machinery that I don't understand, called a Weierstrass transformation, to turn this cubic polynomial that you've got in 2 variables into a much nicer form called an elliptic curve. And elliptic curves look kind of like this. The thing that's really significant with it, though, and this is something that actually came up a lot in my honours thesis, is that if you have 2 points on an elliptic curve, there's a way that you can generate a third one. So let's just say that we pick this point here. Let's zoom in on this. Say you pick this point here and this point here. If you draw a line connecting those 2 points, it will intersect the curve a third time. And then what you want to do is don't take the intersection, but take its reflection. The reason you want to do this is that if they're actually expressible as fractions, the points where you've got your first 2 intersections, so too will be the reflection of your third one. And this operation that you can do allows you to map out all of the points on this curve that are exact fractions. This doesn't seem to be particularly useful yet, but what that then allows you to do is, given one solution to the problem, or given two of them, you can generate new ones using this what's called a group operation. And by doing this, you can then recognize that if your points are in a certain point on the curve, so I think it's roughly there to there, plus there to there, plus there to there, then they'll all be whole numbers. They won't necessarily all be whole positive numbers, but they'll be perfect fractions. And what you can then do is, if you start with one solution, such as, for instance, the one we've already found, the 11, negative 4, and 1, you can then find the point that corresponds to that on this elliptic curve, which is, again, part of this that's beyond me. And from that, you can generate a whole bunch of other fractions on this elliptic curve. Do this for long enough, and eventually you'll find that the one that corresponds to starting with this point that you've already found, and then adding it to itself 8 times, so basically multiplying the point by 9, will end up giving you a point that corresponds to the solution that you actually want. And that solution, which starts with this point here, this is your 9 times the starting point, generates the, when you convert it back, when you sort of undo the rotation, the Weierstrass transformation, it then gives you the final solution that you see here. So we have the apple is equal to this top number. You know, these are all 80-digit numbers. I'm not even going to try and pronounce them. The banana is equal to the second number. The pineapple is equal to the third number. You can permute them however you want, because it's a symmetric equation. So if you prefer to have the pineapple be the smallest number, oh sorry, I said the pineapple was the smallest number. Prefer the pineapple to be the largest number. You can make that happen. Make this the pineapple, this the banana, and this the apple. That's up to you. But the thing that really intrigued me about this problem was that something that seems so simple, so basic as this problem, can generate such a messy solution. What's really mind-blowing about this is that, according to Amit, and I do believe him because I haven't checked his proof line by line, but I've had a look at the overall line of march that he uses. These are actually the smallest numbers that solve this fruit math problem here. And that's why they end up as my mega favorite numbers for the purposes of this little YouTube challenge. Anyways, this was something that fascinated me. If it fascinated you, then great. If it didn't, then by all means, have a look at, maybe post up something that you like yourself as your own mega favorite number. There's probably going to be a bunch of questions about this. I'm going to link Amit's full proof here. This is from Quora, and it's an open source document, and it's his full proof as to the solution. It is missing a couple of steps because he doesn't go into all of the mechanisms of the Weierstrass transformation, which is a part that I don't understand. But there would be plenty of information about that available online if you do a diligent search for it. Anyways, gonna leave it there. If you've got any comments or questions, definitely fire away below. Otherwise, I hope you have a good one.